Today we're going to start talking about reinforcement learning. It's funny how the pendulum swings, but I was just saying that last year I felt bad about waiting till lecture 18 to talk about reinforcement learning, and this year I'm not sure if anybody cares, so and who knows what next year is going to be, right? But I think some people are incredibly excited. I think it's an incredibly exciting topic. Let me try to do what I do on good days, I think, which is to bring back the last ideas from the last lecture and kind of fade into the ideas from today. So last time we talked about the visual motor policies, right? For me, I think it is now clear that I want policies that I will no longer be happy if my policies don't read from the cameras and make decisions at high rate. I think we've seen something good happen there, and we should continue to try to do that. So, the way that looks in our world here is maybe I have the manipulation station here. It has a bunch of output ports. It has the EWA state, the WSG state, but it also has some cameras. And then we put that broadly into a visual motor policy here. And that's what's going to send ultimately back into my EWA commands input port, my WSG command input port. Right? The idea is we want to build controllers that can go from pixels all the way to, well, these positions, maybe not torques. That would be crazy. There's reasons why you might want to do torques, but in a lot of our cases, positions are going to be good. And we talked about the various ways you could think about what's inside this box, including maybe everything we've done in class so far sort of fits inside this box. But the huge promise of trying to get these with tools that are more based on machine learning was, the huge promise, let me just write as I say it, of ML in here is that maybe I don't have to do anything in the middle of that assumes a state representation. For me, that's the biggest deal is using learned state representations. Right, that I don't know how to write the state of the peanut butter on the toast. So with a lot of the classical tools, I would have to impose some representation of what's happening in the world in the middle of this. And maybe with some of the tools we're talking about in the last lecture and in these upcoming lectures, I don't want to do that. I don't have to do that. So we could say that, like I said, everything we've done in class so far, where I maybe have a state estimator and a motion planner and a low-level controller, that could all be inside, and I would call that a visual motor policy, but I only be happy calling it a visual motor policy if it was really making decisions based on that camera at high rate. Last time we said a simple way to start thinking about what visual motor policies can do was via behavior cloning, where we really just took in, for instance, the EWA state and the cameras, WSG and the cameras, and we put it into a big neural net, and we output the EWA command from that. Right, and we talked about the sort of characteristic architecture of that is you maybe have an enormous network to deal with the camera input because it's a very complicated input, and maybe pre-training on ImageNet makes sense. And for all the reasons, we might have an architecture that has a big network to deal with the images, but then you bring in your EWA state, your WSG state, where you have sensors on them directly. You shouldn't have to only get that from cameras. You know, those are easy sensors to add in, and then maybe a relatively smaller policy. In BC, we would collect input and output of this directly. From human demonstrations, let's say. Right, and so if we really just have a bunch of samples of the data here and the data here, then I have a standard supervised learning problem where I just want to find a function, or potentially a recurrent network, if I want to think of it as a sequence. I want to find a function that predicts the EWA command given the inputs that I'm seeing. Okay? That was last time, and I think there's a lot of promise in that. We're seeing like some of the best demos in the manipulation world today are using that pipeline. But we also have, these are some of the ones from our group, but we also know that there are limitations to that. So it's a big open question about how far that takes us in the grand scheme of things. How much is imitation learning going to be part of the final answer? That's maybe one question. And maybe a slightly different question is, do we only need behavior cloning to get to the broad manipulation systems that we are looking for, right? And maybe if we get cool enough haptic interfaces, then then all this stuff starts to work. We don't know. Okay, so that was the backdrop. Now enter reinforcement learning. How does reinforcement learning compare to that, right? So this was a large requirement, right? To say, the burden of these demos, of doing a great behavior cloning demo, starts with collecting lots of human data, collected on the day of your demonstration, collected with experts, right? This is a high cost. Just like in supervised learning, there was a high cost initially of having somebody label every pixel in your data set, right? The cost of labeling or the cost of demonstrating becomes very high. And if we can't generalize broadly beyond our demonstrations, then there's limits to how valuable that can be. Okay, so a harder version, but a super interesting version, is to try to describe what we want out of the system, not with specific input-output pairs, but by saying just what we want the robot to do over the long term, right? And that's what reinforcement learning is doing. In fact, that picture up there is the classic picture you always see in RL. Right? You see, they don't always call it the plant, but I'm going to keep calling it the plant, right? Maybe it's the world or the environment. So my visual motor policy is my policy. My manipulation station is my plant. I have my observations coming out here. I like to call observations Y, right? You could call them O if you're more CS inclined maybe, but these are my observations. Right? Over here is U for me, which is actions. And we also have one other thing involved, which is a reward, R, which you'd like R to be some function. This is the, let me even say clearly, this is the one-step reward function. Okay, just a scalar function of the current observations and the current actions. Okay, so a richer way to describe what we want the robot to do would be to write it as an optimization problem. let's say I have some policy, we'll call it pi, and maybe it's got parameters theta, might be the weights and biases of my neural network, for instance. Then the optimization problem I want to think about is how do I maximize over my policy parameters theta the sum of the long-term rewards given that those rewards were generated by interacting with the plant. So this is not maybe what you'll always see in the way you'll always see in RL, but I'm going to write it this way because I think it's consistent. So we're going to define yn to be my output function of my dynamical system, that I've defined carefully. And xn plus 1 is just the forward dynamics of that system. And I have to somehow specify the initial conditions to start that up. Right, so if I was actually going to implement this in Drake, for instance, then I have potentially a whole diagram. It has a context which has its state described, right? It has its forward dynamics that the simulator knows how to evolve. It has its output functions. The diagram has outputs that are pulled from system outputs, right? That evaluates things like the image or the state of the EWA, right? And subject to this dynamical system, generating y's and u's that are consistent, I want to maximize the long-term reward. I think I did it. I was like worried that I would get here and I would write min, and I was going to write cost over here. It's my habit, but I didn't change u and y, but I did change to r, so that's a little compromise. Okay, so this, as I've written it here, this is not just an RL problem. This is an optimal control problem, right? Broadly. And, we haven't spent the many lectures it takes to sort of build up the total toolbox of optimal control here. I could still, I think, give you some useful insights about RL today, but so the other class I teach under actuated, we spend a lot of time thinking about the optimal control problem more broadly and all the ways to think about using this dynamical system to solve these problems. But long before RL existed, there was optimal control, and I would say reinforcement learning is a subset of optimal control, which has a particular characteristic, particular emphasis. Can I say RL is a subset of optimal control? I mean, some people might want to write it that way. Some people might write it. I'm just going to say that. I'm going to stick with that. Okay. And it puts particular emphasis on a few things. In the library of optimal control tools, the RL methods emphasize, first of all, black box optimization. So unlike most tools in optimal control, the RL algorithms, I think people know, are not going to assume necessarily that we know f, the function f, or the function g, or even the function r, only that we can get samples from it, right? So we don't need to know the structure or the governing equations. I just need a simulator that will tell me the output, or a real robot that will tell me the output. And the other thing that it emphasizes strongly, partly because it wants to connect to the real world and to data, is the stochastic aspects, stochasticity. So stochastic optimal control would be if I wanted to maximize over theta, for instance, the expected value of my rewards. Okay, And I think there's lots of ways I could discount this or do average rewards and stuff. I'm just going to keep it at the high level for now. But and it's interesting to think, okay, so this, I haven't written anything that has probabilities yet, so how does that enter in my equations? So my output functions can take random variables. And my dynamics functions can take random variables. And we've already done this a little bit, actually. This is also a random variable. And I can start my initial conditions in general from some probability distribution. Okay, and once I pull any one of these would be enough. Once I make the initial conditions come out of a random variable, then suddenly the future state is a random variable, and the future observations are a random variable, and it makes sense then the reward is not a random variable. And if I want to maximize a scalar function of a random variable, I need to take some measure of that random variable, and the most common one for lots of important reasons is to take an expected value. So this is I think the way to connect the modeling that we do. Oh yeah, please.
In that f,
yes.
It's xn, and in that f is xn.
Oh no, it's not. It's just too many symbols coming out of the typewriter. Yep, thank you. Yeah. So this is I think a very nice match to the modeling, the modeling power we've been talking about in Drake's systems framework, for instance, and the way we've been writing simulations and the way you would generate this. There's one thing that is missing, actually. There's another way to add randomness besides just the initial conditions and sort of noise. That's a really rich specification. Even if I were to restrict myself to Gaussian noise coming in, once I have a nonlinear f, I can do anything.
Sorry about that. I don't mean to interrupt, Professor. We're from MITAB. They can't hear you on the lecture capture. Check on your mic.
Thank you very much. We've stopped using that. We just record ourselves.
I apologize.
Okay, cool. Thank you. Yeah. So even if this is just Gaussian random variables, since I'm multiplying it by an arbitrary f, I can do really rich things with that. But there's one thing that I think is missing in that standard math. Anybody know the thing I think is missing? We'll see it in the code in just a minute. But yeah.
Do you need a penalty of some kind?
Okay, there's definitely a reward that's in here. Oh, okay. You might say the thing that I'm missing constraints. But you can make reward up. In reinforcement learning or any of the unconstrained optimization, you would take the constraints you might have in a normal optimization and you would shove them up into the objective as a penalty function. So maybe that's, yeah. But I would tuck that inside here. But as rich as I let R be, as rich as I let G be, F, and this probability distribution, there's still something that this model of the world doesn't quite capture. Yeah. Unknown model. I mean, depending on how rich your unknown model is, that could fit. This is a pretty rich specification, right? The policy can be stochastic. That's true. I didn't actually even write the policy. I should have written the policy. I missed my U of n is policy of y of n. And this could be, that was an omission, not a philosophical miss. You're totally right. You called me on it. And this could be stochastic or deterministic. You're totally right. But that one I just forgot to write. There's a more fundamental thing that this doesn't capture. Okay, it's discrete. But I would say if I make my discrete to continuous math, I could make discrete steps small enough that it can capture most. That's not the fundamental one I'm missing. People do it in RL. all the time, but we didn't do it enough, I think, in classical control. Which, a particular type of randomization, I think, has happened in RL that didn't happen in optimal control. If I made like a random number of objects appear in my world, then even the definition of X is different. The number of state variables is different. And so I don't quite know how to write that here. There's like a distribution over the size of X. And that kind of breaks my otherwise beautiful state space view of the world. You can still accommodate that in the tools we'll build today, but this is like almost perfect, but there is something that it's missing, which is that I really could have, in random draws of my simulator, a completely different state, a completely different number of objects in the world. That's the only thing I find unsatisfying now about writing it that way.
But you can always make your y fixed, right? Y observation.
I think it must, apart from clever network parameterizations and stuff like this, but I do want y to be roughly fixed. I think it's x that gets, bigger or smaller. If y is a camera, right? If y is my camera input and my robot data, then that doesn't change even if I have different numbers of objects in the scene. But x would be a different size. So the generating equation.
Maybe in RLX could be like a list with variables.
Yes.
Like if you think f can be very general functions, size for lists.
Okay, so if I were to, so maybe you say that this, if I was thinking of this as like a general data structure, then everything's fine. Yeah, only if I'm thinking about this as a vector space, then it, and a difference equation on a vector space, then it's impoverished. But if this is like a dictionary in Python, then I'm good again. And that's maybe a good way to think about it, is I need to go from like my comfortable vector space world to like a dictionary in Python world. And that kind of, messes with me. But it's important. It's an important change. Okay, so let's just, take a second to appreciate that this is harder than BC, right? So behavior cloning is here. I collected directly input-output data. But this is a harder problem than BC for a subtle reason. Because BC can do sequence learning. If I'm going to train a LSTM policy for my cloning, then that's actually got some temporal components to it too. But RL is harder than BC. This is supervised learning, right? Even possibly sequence learning. But BC doesn't have to think at all. By having the data before and after my policy curated for me, it doesn't have to think at all about all the stuff that happens inside my plant. It just completely removes completely avoids the plant. And a lot of messy stuff can happen in the plant. Right? Inside our manipulation station, we have the physics engine, we have the geometry engine, we have the contact, we have the renderer. That's a lot of messy stuff that our algorithm's going to have to go through now. And BC just skips all that. The classic way that people would talk about RL being harder than supervised learning is the delayed reward problem, that you have long-term consequences of your actions. The sequence learning has some of that. So I de-emphasize that here, but there's another, just the fact that my reward depends on my long-term, even my reward, my instantaneous reward at time 23 depends on all of the actions I've taken from time 0 to 23. Whereas in behavior cloning, certainly in the simple versions of behavior cloning, a feed-forward network, it just depends on the instantaneous input. Okay, but this is such a powerful general framework, this optimal control framework, the RL framework, that people are, and it's had some incredible success. So AlphaGo, for instance, You know, there's just so many, StarCraft, you name it. There's like incredible successes of RL. And we've seen some in manipulation too, right? So the one that everybody talks about was the initial one by OpenAI, but now it's been recreated in a lot less time. And it's super compelling to say the recipe to make an advanced robot manipulation system is you just make the simulator, and people have simulators, right? We just write the cost function and then you do deep RL, right? And people say things like, it's so nice we don't have to do control anymore. Control is hard, and I just don't have to do that anymore, right? But it's not completely all done, you know. And like I said, there's the pendulum swings around, and people seem, even though RL is incredibly powerful, I would say this year people are a little less excited, and I'm sure next year they're going to be super excited again, right? But there are shifting winds, and people are, you know, there's various levels of excitement in RL. I did my thesis in RL. I don't know if you guys know that. I had a little walking robot. I couldn't afford a full piece of rubber, you know, so I had to cut out, I had to use other piece of rubber one day, and I never had a new one, so I had like very humble beginnings, I guess. This was a CD rack that was holding up my ramp, right? And then, so that's just a mechanical toy that would walk down a ramp. And then my thesis, dating myself now, was a robot that learned how to walk because it was close to walking by falling down a ramp, yeah? And I have a secret. The only reason I put this in here is because Boyan's about to throw away my treadmill that's been sitting in the lab corner. And I was like, I just want to show it one last time, you know, for nostalgic reasons. No, it's good, it's good. This is the thing, like, so if you're doing an RL thesis, right? So for me, I was like writing my thesis here, right? And there was a treadmill here, and all day long, you just kind of hear this. You know, it's like, oh my God, every once in a while you hear, and then you'd hear it go, you know, as it was, the treadmill shoved it up against the wall, right? But that was my beginnings, I guess. And you know, I don't use RL a lot to make robots move today, but that's not because I don't think it's powerful. I think it's there's a pretty subtle reason, and maybe we can come back to it in later, but I just don't enjoy the state of it right now in that way. But you know, like, I don't want to tune cost functions and stuff. I'll say that more carefully as we go. We are doing RL theory because I think there's some beautiful things that have happened in RL that need to be understood more rigorously. So the group is actually doing a lot of RL, but just maybe when we want the robot to do something, that's not the tool I turn to today. Sorry, yeah, right.
Can you talk a little bit about the runtime with optimal control as RL?
Yeah.
I know it was like unbounded if you have the runtime. With RL, how does that?
Okay, good. So I think people have the impression, like, the OpenAI was massive amounts of compute. It simulated, you know, millions of years of finger twiddling in order to do that, and people have gotten that down. NVIDIA has a version now that's doing a very similar task in dramatically less, at least wall time. I think a lot of compute still. Optimal control isn't immune to that. It depends which versions of optimal control. So linear optimal control is immune to that. Nonlinear optimal control, there's many different approaches, which I think RL is one of them, and they enjoy different levels of generality, like how many different problems you can embrace with that, and how strong is the algorithm, right? So RL is all the way on the side of you can optimize any plant and any cost function, but it might take a long time. And if you say, I don't want to do any, I'll carve out a smaller set of problems that I want to focus on, then you can write narrower, more efficient algorithms. And the big question, the big money question is, where is manipulation in that space? Is manipulation so complicated that you have to treat it with the, you know, anything algorithm, or is there enough structure in the manipulation problem that more targeted algorithms should be used? Okay, so my plan for today is to talk basically, you know, I don't have all of the optimal control background, you know, that we've developed, but I could still talk about some RL examples, and including the sort of software back, how do you write these things? And then I want to talk a little bit about RL from the optimization perspective, because we've been going back to optimization, using a variety of optimization tools, and I think we can connect to that. And I've got, as much as we have time to say about that. Let me start by thinking a little bit about the software, right? So, how many people know OpenAI Gym? It's a great thing, right? So, everybody agreed that there's a relatively simple requirement to define an RL problem. You just have to, define your observations, define your actions, define your reward. And the community, finally got behind a particular interface. Just someone agreed that these are the function names in Python that we should all write our code behind. That way, anybody who's writing simulators or problem instances on one side can present this interface, and everybody's writing RL algorithms on the other side can act on that interface. And Gym, the OpenAI Gym, is the interface that won. It's maybe transitioning to Gymnasium. We'll see. OpenAI kind of did a mic drop on it, said we're not going to do that anymore, and someone else is like, that's still important, so maybe, and we'll see if the world moves to Gymnasium, but I think it's got so much momentum that we're not going to lose it. So the software interface to this optimal control problem is just, you have an initialization of your environment, your Gym environment. You step, that's my, f of x. You can reset if you need to. You can render. The step also actually, it takes the action and it outputs both the observations and the reward, maybe a close. All of those have a direct mapping to what we've been doing all term, right? So, your init is just build your simulator. The step is just an advance to in your simulator, and then evaluate your observation and evaluate your reward, for instance. And reset might just be resetting the context in our setting, right? So everything, this is just, and anything, any simulator can easily present this interface. That's the point of it. It could be an Atari game, it could be Go, it could be a manipulation station. Render is like the Meshcat publish kind of idea. To make it easier to go from that diagram and get it all correct, the actions and observations and rewards, we have a thing currently in manipulation repo. It's slowly moving to the main Drake, which is just the Drake Gym env, where you can hand it a simulator. You can tell it which ports are the action ports you care about, which ones are the observation ports, which one's the reward port, or you can write a function for the reward if you don't want to use ports. And it'll wire that up and make that for you. Okay? So it just makes that easy to make that interface. And then, so that's the OpenAI Gym, and a lot of people knew that, but maybe I could have written it more carefully. So this is my step, reset, whatever. And then on one side of this are the simulators, for instance, or a real robot if you so choose. And on the other side of this are the algorithms. Only one simulator will be discussed today, unfortunately, but there are other choices that are perfectly good. On the algorithm side, similarly, I'm just going to pick one because I don't want to talk about all of them. These days, we mostly use stable baselines 3. Which is a nice implementation from DLR, right, I think, and that has a lot of the, kind of like OMPL had a whole list of motion planning algorithms. Stable Baselines has a nice list of reinforcement learning algorithms. And this one is written in PyTorch. A surprising number of our libraries never made the leap to PyTorch. And it's a perfectly good implementation. It's the one we use. It's interesting that the algorithm that most people use, or that we'll talk about the most today, is PPO. Maybe, what'd you say? Yeah. SAC. Right, so let's distinguish. So in terms of the algorithms, in manipulation, for instance, there tends to be a breakdown between, if you're using simulators, then PPO is often a go-to, SAC maybe, but if you're using real robots, then people tend to do Q-learning kind of things. I think really the distinction is, with a simulator, you worry less about data starvation. You run your simulator fast enough and you don't curate your data carefully, and you do online RL. And with real robots, data is precious, and you don't want to have to run 100 million trials, so you do offline RL a lot more, which is more compatible with Q-learning type approaches. So you store every piece of data, you reuse the data to update your policies even after it's not the same policy that's running. I'll get a little bit into that distinction later. But PPO seems to be a fairly dominant entry now. PPO has become the default. See, I backed it up. Reinforcement learning at OpenAI, and just a lot of people do. In fact, it's not just PPO. It's like there's a particular commit in a particular repository that has a particular set of parameters for PPO, and those you should only use that one. Because people have done like studies of saying, we took PPO, we did huge parameter sweeps, and we got all kinds of different answers, and then we did git bisect on the original PPO repository. We found out that this is the commit that everybody should use. And then like another paper found roughly the same thing. So it's like the world just tried to implement exactly the policy parameters, the optimization parameters from this one commit. Don't mess with it. You're going to spend a lot more time optimizing. Okay, so but that actually is nice. You know, kind of weird way that's nice, because then you know if there's just one version of PPO that you should care about, right? So like if I wanted to type in PPO and just be happy, I'd like, as long as I use the parameters from that one commit, I should be good. I should have the same performance as other people. And Stable Baselines has used that commit, for instance. Okay, so let me do a little example. I think it helps to put the stuff in context, right? So remember the box flip up. I thought that was just such a compelling example for force control before, right? So let me just even remind you of our existing example for that. This is the old notebook where I'm gonna run the stiffness control version of that. Not the force-based, I'll do the stiffness control-based, and I'll just do the version that was scripted, right? So we had a virtual finger. We programmed the remote center of compliance, if you will, and got this just beautifully simple high-level control. Just says move it towards the wall, start lifting it up. The center of compliance goes here, the box will flip up, and it'll pull itself back down, right? That was just like a really nice way to flip up a box, I guess, if your finger was a point. Okay, so I did that again in RL, right? This morning I just thought I'll code the exact same environment and I'll put it in my Drake gem and then I'll run PPO on it, and I did. So let's see what happens. I'll restart that so I can use the same Meshcat instance. So I'm going to just use the pre-trained model. It doesn't take long to train this one, a few minutes, but I'll just use the
mostly so I don't run out of batteries here. I'll use the pre-trained one. Okay, so it flips up the box very well, and then it smashes its head against the side for the rest of time. It'll get random resets, okay? It flips up the box, and then it smashes its head against the wall. And I got to the point I was like, oh, that I could tune that away, but it kind of makes a point. That's like it's pretty good, but it's annoying, that way too, right? So, I mean, I didn't like tell it to smash its head against the wall. I'll show you the cost function, right? Okay, that keeps going. All right, so yeah, I recorded it just in case. All right, so let me just sort of step through what that looked like, and you can ask as many questions as you like. But so what was the network in that? Okay, first of all, maybe I should have started with the action space. So I wanted it to have the advantage of stiffness control. I didn't want to like deprive it of stiffness control. So the input was actually because if you remember, if your finger's a point, the difference between stiffness control and inverse dynamics is non-existent. It was just a 1 over mass. But so I basically gave it that should be export input. Inverse dynamics desired position was the action space. Okay, so that's like the virtual finger in the stiffness control. The observations was direct state output. So I'm not even doing visual motor yet. I'm just giving it access to the true state and asking it to learn from that. And then I just used Stable Baseline's default MLP policy to go directly from state to actions. Now we should expect that to be enough because the optimal control for that problem should be just a function of state. I didn't have to use an RL. I didn't have to use a recurrent network here. I think just a multi-layer perceptron policy feed-forward network is enough. And if you look at the default MLP policy, which is actually like all the examples use the default policy. It's kind of a weird thing in RL for control. Is people basically there's like maybe this one and maybe one with 255 units in the middle, and they almost all use these same network parameters. And people really don't change those very much. My instinct would be to start mucking with the size of the network a lot, but people really don't. So the default network architecture from Stable Baselines is just that. Okay, so that means the policy network has 64 hidden units, so it has the observations, which in this case was the state, mapped into 64 hidden units, and to the output, the action. The value function was roughly the same, was basically the same size. So PPO, I will get to it as I go into it a little bit. PPO is actually an actor-critic algorithm. So it has both policy parameterization and a value function parameterization. Okay, and then I told you that the way that you make that in the Drake GymEnv is I just have my plant. It's a little smaller than I would have liked here, sorry, and I have an inverse dynamics controller. I made a super small function for my reward, and I piped that to the reward output. I took my state, I put that to the observations output. And the actions were almost just directly the inverse dynamics controller, but my inverse dynamics controller wanted a desired state, and I only wanted to give it a desired position, so those little boxes just put 0 for the desired velocity. Okay? But it's really just like make your little diagram, pick the input that you want as your actions, pick the output that you want as your observations, output or cost or a function to be the reward. The cost function is kind of fun and interesting. I really didn't do any cost. I mean, there's one thing I did to do cost function tuning, I would say, which is this last line, but I'm like allergic to cost function tuning. I don't want to do much of that. I did it before, and I don't ever want to do it again. It's basically the box angle. Okay, I wrap it around because sometimes it did play tiddlywinks with the box, and it would do multiple spins and land upright. So I'm okay with it. I'll take that as a success. So the box angle modded into pi. Okay, and most of the cost is just saying that I want my angle from vertical to be small. See, I do think about the world in terms of cost, not reward, and I put a minus sign when I'm handing it to my RL algorithms. That's just how I roll. So I penalize the angle from vertical, I penalize box velocity, I penalize the effort, which is the difference between the virtual finger and the actual finger. I penalize the finger velocity because I don't want it to be going like that, but it still did. And then the 10 is the one thing I was like, I didn't type it in the first time, and I had to put that in. And you can see the comment why. So if I only had negative rewards only, and the Drake-Jim-Env will terminate if the simulation crashes, right? It'll terminate early. If every time step can at best be a negative reward, then it wanted to crash the simulator. It was learning to break multi-body plant, okay? So I had to add 10 so that every time step was positive, and then it would be rewarded for running a long simulation and not rewarded for crashing my simulator, right? How do you crash the simulator? You like cause ridiculous penetrations with, at high velocities and stuff like that. And it was learning to do that. That's cool, but it's annoying. So anyways, but that was the one thing I was like, okay, I have to go back in and add a 10. Everything else was like, I don't know why I picked 2 and 0.1, but it wasn't tuned. That was just me thinking that was 20 times as important as that. Yeah?
What was the effort?
The effort, in the stiffness control, I chose effort to be the distance between the desired finger and the actual finger. So that's like the stretch of the spring. Yeah?
Why 10? What if you do 100?
I just looked at the rollouts and saw what the largest cost I could get with those other things. My one-step costs tended to be between 0 and negative, 5 or something like that. I just added something that was safely bigger than the smallest reward I had gotten, just to sort of shift that up to be in the positive space.
I think the default stable baseline might also just normalize to be 1. So we need to do
No. It does roll normalization, but stabilize baseline does that for like computing purpose, for the feedback. But like if you still need to change that for this too. Does the environment like go forever, not crashing?
So the comment there, just to say back for people watching remotely and the like, is that stable baselines certainly recommend strongly that you normalize your action space, you normalize your observation, maybe less about even observations, or normalize your reward. And it does some amount of automatic things depending on if you turn that on or off. So the question was, does it even matter if I had picked 100?
The intuitive interpretation of what Leo just mentioned is that although it does, so now we are trying to make the reward positive, right?
Yeah.
So this positive is using 0 as a baseline, as a decision boundary
Yeah.
for crashing it or not. Even with normalization, it will normalize that baseline equals 0 as well. So your baseline is no longer 0, it's something else. So you need to be above or below that new threshold for its behavior to change. So normalization doesn't matter.
Yeah, normalization wouldn't fix it wanting to crash the simulator, right? Yeah. Good. Any other questions about that? I definitely could have made that better. It was a teaching moment for, I just thought, I'd leave that. It's kind of like, because that's real. I mean, you'll do that. You'll see robots like smacking their head against the wall and stuff like that until you tell them not to. And I want to think about, that's like, well, let me distinguish between 2 different types of that kind of behavior, right? Some of it is power in the sense that it can find very strange solutions, and some of it is bad behavior by the optimizer, I would say. So when it comes to like tuning, so if I wanted to make that better, I would probably, that basic framework is probably okay. I could maybe make the 2s and the 0.1s different, and I could dial that in and get a behavior that was less, right? If I'd really penalized action, then maybe it wouldn't do that, okay? But let me distinguish between 2 types of tuning. I won't write the word distinguish. I was only going to write reward tuning, but I wrote cost, and I'm like, I'll just go with it. I would say the first one is whether you've fully specified the task, okay? And I'll contrast that with reward shaping. And this are slippery slope, okay? So let me distinguish what I mean here. So it's actually hard to write a cost function whose optimal solution has the behavior you really want. I gave an example of that before when we were talking about loading the dishwasher, right? I didn't tell the robot, don't throw dishes across the room, right? And if I didn't tell it that, if it could throw the dishes into the dishwasher, it probably should, right? That would optimize the objective. So I would say that's my fault. I didn't specify the optimization function whose optimal value had the solution I want. And it's not because I'm a bad person, it's because it's really hard to write good optimization landscapes, right? And in general, I think a lot of the behaviors that we do as manipulators, as humans that do manipulation, is due to a lot of common sense understanding about the world. Like, dishes shouldn't be smashed into the plate, into the ground. So like you don't have to, having to tell all of these, Leslie Kelvin likes to call it background utility functions into a robot is very, very hard. And I think it's really interesting and hard to think about how do you give the programmer the vocabulary to specify the super rich semantics. And I'm all for that. I like that a lot. I think that's an interesting problem. And I think, and so like natural language can help with that, large language models, foundation models, these are things that are gonna help us make progress on that. There's a second thing which happens, which is just you're helping the optimizer. Okay, which is that the optimizer got stuck in a local minima, and if I write the cost function a little differently, then maybe it'll do better and it'll get down to the right solution, okay? And this one, I choose to do less of this and try to work on better optimizers instead. That's just my preference, but so this one I have less excitement about. This one I think is fundamental and good. So for instance, like which one, if I were to start tuning that example, my box flip example, which one do you think is more the problem there, right? Yeah.
I guess there's both. Like,
There's probably both, yeah.
You didn't tell the robot that it shouldn't smash itself. And so like I guess that component is missing. But then if you wanted to like I guess improve behavior somewhat, then that'd be word shaping.
Nice. Yeah, so I didn't actually say don't smash yourself into the side of the bin repetitively. That's my bad. I could have said, I don't want you to smash yourself. My bin is important or something, okay? But there's also, I did tell it, all other things equal, use less energy, or use less effort, and keep your finger velocity small. And it still chose to go like this. So I'm pretty sure there's a solution that would have flipped it up just as well that didn't go like this. And so, yeah, in that case, I think the optimizer has done a good enough job to get the job done, but it hasn't found the optimal solution. And just so you see the world through my eyes a little bit more, let me take the opposite extreme of that, right? So when we talked about the graph of convex sets motion planning, the cost functions there of like this, the bimanual thing doing complicated, there's a start, there's a goal, I want the shortest path. Subject to velocity limits, acceleration limits on there. The optimizer solves the global optimality, or it says there's no solution, right? That's just, it's hard, there's only a limited class of problems that we know how to write that have a strong solution like that, but the joy of working with that system is more for me than when it's, when you have to do this, right? Yes?
You think if you train it longer, would it not to smash itself?
Yeah, that's a great question. I suspect it would continue to get better, yeah. The question would be like how long and what, but yeah, you're right. I think I could probably have just let this go. I did that fairly long for once, and it didn't change a lot, but in that particular example. But I do agree. I think you could, I mean, fundamental to RL is a little bit of exploration, and as long as it's still exploring, it could eventually hop itself out and keep getting better. Great question. I mean, to some extent, what we're doing is we're lifting up the programmer from, you know, so like, I can make a robot do anything using GCC or Clang. Right? If I just have to write C++ code, and if I write good C++ code, I can make the robot do anything, right? And that's true of RL too. If I can write a good enough cost function, I can make the robot do anything, right? But in C++, you know, the compiler is deterministic, and you know, and it's fast, and the error messages are clear. And I think RL will get there, but right now RL is such that you know, you try your cost function and then you wait a while, and it's more frustrating to work on. But that's just an intermediate state, and that actually, I think those of you that are working on RL, I think you should work on that, because that's super. Like, there's just better things that will happen as the field continues to work on it. And the fact that it's solving problems that nobody could program, well, that's hard to say, but people have not written GCC programs to do some of the amazing things RL is doing. So it's lifted our abilities. I would put like kinematic trajectory optimization somewhere in the middle between those two, right? So you're going to have to do some amount of tuning with kinematic trajectory optimization. A lot of times you can do it with like an initial guess, or add a constraint to say, oh, you know, I didn't want you to do this crazy thing that you chose to do, put a constraint on there, and then you know, you could shape it in that way. And I similarly find that very annoying, and I wish that we could just have stronger optimizers. So there's a whole spectrum, I think, of these algorithms. Okay, quick stretch. I wrote to myself, don't forget to tell people to stretch. Okay, so let's talk a little bit more about at least the optimization view of sort of the PPO class, or maybe even simpler than PPO view of optimization. So we've talked a bunch about optimization. We've talked about nonlinear optimization. We've talked about some convex optimization. In general, let me say if I've got some parameters, and I'm going to just call it F for my parameters here, and I've got some complicated landscape, right? And I want to try to find, I'm going to stick with minimum because I'll screw it up all day long if I don't. Right, I'm trying to find the minimum of some non-convex objective function. And really, in the discussion today, we're going to have this be unconstrained optimization. We're not going to add additional constraints, okay? If we did have additional constraints, we would push them up into our cost function with a penalty method, like an augmented Lagrangian or something like that. We've talked about various ways you can optimize this. Maybe you find an initial guess and you start moving downhill based on the gradient, right? So we've talked about gradient descent. Now, gradient descent, as we've talked about it so far, is off limits. It's not allowed today because it required us to be able to evaluate the gradient of that function. And that means I needed to know something about this. This is not allowed in the black box view of the world, right? Because if I'm going to play Atari or Go, and or let's say StarCraft or something like this, I don't have gradients coming out of my that simulation, that game engine. We talked about sequential quadratic programming. That's what SNOPT is doing when we're solving IK problems or even kinematic trajectory optimization problems. It similarly is using partial f, partial theta. You would think, since it's doing quadratic programming, that it would also be using the second derivative, but actually it's making an approximation of the second derivative and only asking for the first one. Sometimes to its detriment, but also requires that. The question is, how do you do optimization if you're not allowed to get the gradient? Okay, and RL has black box optimization in general has a bunch of interesting solutions to that. And RL has particular versions of black box optimization that are very well suited to the RL domain. Okay, so what do I mean by black box? That means I have, let's call it f of theta here, right? I have access, if I give it a theta, I'm allowed to evaluate f. I get the value of f. But I don't get to know anything more about f. I don't know if there's sines and cosines in there. I don't know if anything. As far as I'm concerned, theta goes in. I can't see behind the curtain. The f of theta comes out. And I have to write an algorithm around that. You would contrast that with, people call it white box optimization or glass box, maybe makes more sense. Glass box optimization, where you can see everything. I mean, this is, so the reason, so like, I think it's obvious that that you can make Drake look like an OpenAI gym. It makes me a little sad to do that because the whole point of Drake, right, is to look inside F, right? Drake is a differentiable simulator. It can give you partial f, partial theta, even if you run a whole simulation. It's not just the dynamics of multi-body plant, but you can take gradients through simulator advanced too. You can put a gradient in, get a gradient out, right? So all of those things are available. And we're going to throw them away when we're doing things today. And it turns out I haven't yet been able to do much better with gradients. Maybe I'll have to get to that next time, but that's the game, black box optimization. So how do you do black box optimization? It sounds like, how could I do anything without a gradient? But then if I tell you how they do it, it's like, of course. Right? So let me give you the simplest black box optimization, okay? I'll take theta at time 0. Okay, this is my this will be my optimization step. Okay, so every time I'm going to run a simulation or something, I'll increment my theta estimate by 1. Okay, so here's a simple algorithm. I'll evaluate f of theta I plus some random noise, okay? And then maybe I'll also, for good measure, I'll evaluate this. Turns out you don't have to. But I'll evaluate this. And if the random vector I chose was better, I'll keep it. And if it was worse, I could keep this. Turns out there's even funnier things you can do, okay? So not a huge brainstorm algorithm here, right? It's just, I'm going to say, I've got an initial guess. I'm somewhere on the landscape. I'll evaluate it here. If that was better, I'll keep it and I'll move down to here. If it was worse, I'll stick with this one. Okay. More generally, if I were to say theta I plus 1 is, let's say, I'll write it into discrete logic, but we can do it more directly in a second here. If f of theta I plus W. This is my experiment. I'm doing minimization because that's how I roll, is less than, right? If I got better, then why don't I update this to be plus W? Now, for reasons we'll understand as we get to the stochastic case, we tend to actually put in a learning rate here. Okay, some small positive number. So I don't go all the way to the guess, because so why is that, right? So if I were to go all the way here, oh, it looked better on this one particular simulation, but when then someone else puts a different mug in the scene, maybe that was a little too aggressive. So I'm going to say, if I did one experiment and it looked better, I'm going to take that as a suggestion to move in that direction, but I'm not going to go full tilt into that one observation. Okay, and there's a stochastic interpretation of what happens with this version of the algorithm, which plays out beautifully. Okay, and then otherwise, I'll go in the opposite direction, but again, I'll put a learning rate in there. That's supposed to be eta. It's looking a little more curly than I meant it to, but that's an eta. Okay. And there's simple versions of this that, instead of writing a plus or minus here, if I just multiply it by the difference of this, I get a version of that too, which will always go in the direction, I can get rid of my if else and just write this as a single line by putting the difference here in here, and that would basically set my sign and actually my amplitude of my update. But the basic idea is take a random guess. If it looked better, let's go that way. Now, that's actually a pretty powerful algorithm, okay? And PPO is doing a very smart version of that, but it's not that different than that, okay? So what would you expect that to do compared to a gradient descent type algorithm, right? Gradient descent would take a sort of direct path, in this case, here. It'll get stuck in local minima here, right? This one will take maybe a more meandering or slow path to get to the minimum, but will have similar behavior. Take some more trials. It could also get stuck here. If we start adding the randomness, it could potentially jump out of here. So it becomes a stochastic gradient descent instead of a deterministic gradient descent. So that's, Don was saying, like, what if I ran it longer, it might have hopped out of here and found a better solution if I ran it long enough, right? So I think that is a pretty decent first order model of what you should think about the RL algorithms are doing. They're doing much more behind there, but just as a very first glimpse of like, how does that compare with the more model-based methods, which are taking exact gradients, for instance. This is doing random gradients. And we're going to have you look at a version of this called reinforce in some detail on the problem set. Some of you already started, yeah. And reinforce is sort of the predecessor to PPO. Okay. So the picture you should have in your head is that you're going to go downhill. You're still doing a gradient descent-based algorithm. You're just going to take a random walk downhill that's biased towards in the direction of the true gradient. And that's actually something that can be made precise, is that with most of these updates, you can say that the expected value of the update is in the direction of the true gradient. And the variance, you'd like to be small, but the variance tends to be big. And we do a lot of work in RL to try to make the variance of the update smaller. Okay? Now, so that's kind of like the black box equivalent of gradient descent, but you can also, you can think of black box equivalents of SQP too, right? You could take multiple samples and like CMAES is called, it's covariant matrix adaptation with, with something sampling. It's what's the ES? Evolutionary strategy, thank you. Evolutionary strategy, yes. So imagine taking lots of random points on your landscape and fitting a quadratic approximation to it, and then taking a second order update, right? These things can be made to work. The picture is clean if the function is deterministic. It's more beautiful, but a little bit more complicated when you get noisy evaluations of your function. Someone could have put a different number of objects in front of me. Every time I run the robot, I get a slightly different answer, and I'm trying to optimize the expected reward. But the background is the same, right? And some of these algorithms enjoy more robustness to that. You can think of it a lot, for those of you that do a lot of supervised learning, you could think of it about like how does your SGD come out of mini batch, right? And some of the optimizers are a little better at handling mini batch. Atom seems to be really good at it, you know, and these are the same kind of things. So we get the comparable algorithms here, which some of them enjoy more robustness to the mini batch. It really is very similar to mini batch. Every time I do 10 rollouts and I get 10 slightly different evaluations from a potentially infinite number of evaluations, it's very much like a mini batch kind of update. Okay, so I thought, I said before that, you know, we do a little bit of work. I'd say we're leaning into the group in various forms of thinking about what RL is doing well, what it's not doing well, how I can combine it with some of the model-based control that we do. So maybe I'll spend a few minutes at the end telling you one of our recent research stories about that, because I think it fits this picture fairly well. But so let's just think, is this a good idea, right? So I told you that I had, you know, like the whole point of Drake was to make it so you can look inside F if you want to. Is there any reason why you shouldn't take gradients if you have them? It's a super interesting question, because here's the mystery, right? RL started to show robots doing things with their hands and stuff that we haven't seen from people who are using gradients before. But with that picture, you'd say gradients should only be better, right? If I have a gradient, why wouldn't you use it? Okay, well, there's a couple reasons why it gets subtle. The first one I think is very easy to see, which is that if I'm doing visual motor policies, it's hard to take gradients through a renderer. So if I go from my equations of motion of my plant, and my output function is render a camera into pixels with a game engine style renderer, and then do a neural network to go back to my actions. The neural network's super differentiable, that's great, it's built for that. But the renderer is not, okay? And there's been a lot of interesting work on differentiable renderers, but renderers aren't different. I mean, you could actually, I mean, if you move to the next pixel, things, you know, you could have an object whose pixel value is, you know, that pixel 14 and, you know, by 28 hits the object, and 13 by 28 misses the object, right? True renderers actually do a little bit of smoothing around the pixels and stuff like that. But if you give me a gradient of how pixel 1428 changes with respect to my parameters, that doesn't do as much as you'd want. So differentiable renders have been great, but not the panacea, maybe. Volumetric rendering like NeRF seems to be a much better way to talk about that, and that's been paying off. But if you just wanted to take gradients, like if I just had the ability to take gradients through Drake's renderer and back, it's not clear that that's going to solve my problems. But if you look at like the OpenAI example, they didn't even have a renderer in there. They were just doing state feedback. And they still did something that surprised those of us that have been working on control through contact for a long time. So what is up with that, okay? And we spent some time thinking about it. Actually, Terry and Max and Kai-Ching spent some time thinking about it, and I can tell you this story in like 5 minutes. It's a great 30-minute version, but I'll tell you the 5-minute version, okay? So take the OpenAI example. If I give myself observations, or state observations, then the major complexity that remains actually is the contact mechanics. And somehow they seem to have done an optimization that was beyond what we had been doing and other people had been doing through the contact. So was there anything happening there, okay? And I think the story that has been emerging is that we knew for a long time that contact dynamics leads to discontinuous landscapes, okay? And I'll say that in the short version of that here. And it seems like the random sampling, the way that people are doing messy gradient descent, is actually smoothing out some of the discontinuities that comes from contact. And that it was a good idea and we should have been doing it the whole time. So actually taking random samples could be better than taking analytical gradients. It's more subtle than that, okay? But we talked about some of the discontinuities of contact. It doesn't happen everywhere, but it does happen if a small change in my gradient, or in my initial conditions, for instance, causes me to hit a different face of the robot, of the environment, for instance. Okay, and that leads to these simulations that could have, so you could imagine if I change the initial conditions, and I now look at the final conditions, I could have a very different final condition. If I've moved the initial conditions along here, I get a very different final condition. I'll end up on one side or the other. So I could get a very different reward if I went one side or the other. So that would be a very discontinuous, so it's not this picture. It's this picture with just immediate jumps, right? Can happen if I have contact. You also have these weird artifacts from simulators. Remember I talked about how you can be going inside one, the simulator's pushing you back towards one face and then you're all of a sudden pushing you back towards the other face. I think this one we should just resolve, but this one causes some problems too. Okay? And if you look at how people in optimization theory, forget about RL, optimization theory, think about how to do non-smooth optimization, they have known for a long time that first of all, non-smooth optimization landscapes can screw up gradient descent. It can screw up even convex optimization, otherwise convex optimization. And a natural idea would then be to smooth the objective. Okay, so if you could take this and draw, if you could somehow take your cost function and just like average over it and get a nice smooth version of the cost function, then wouldn't that be nice? Wouldn't that make things better? It turns out there's an interpretation that the way people are sampling in RL is doing that to our cost functions. A bit, okay? It can move the minima. It can do. There's a lot to think about in this world, right? It changes the optimization landscape in some ways that might be better for finding a solution, but might not find the optimal solution. Okay. So you can take these things that we get out of actual contact problems and see that they get smoothed out with RL type sampling. Those are actual mechanical examples. Okay, and I'll skip a little bit here. So then the question is, if you have the analytical gradients, should you use them? And it's actually very subtle because there's times in your landscape where you're in smooth sailing and you should definitely use a gradient if you have it. There's times where you're very close to a discontinuity and you prefer the black box methods. So we've been thinking about ways to take the best of both worlds. And you can actually, if you compute both the empirical gradient from a RL side and the analytical gradient, you can actually do a little numerical test to see if they agree and know if you should trust your analytical gradient or not. Okay, there's games like that are actually super interesting. One last point I'll make because I know I'm out of time. Okay, the coolest thing though is that once we realized that was helping the optimization landscape, you could stop and think, okay, well, did you actually need to be random to get that effect? And no, you can actually just change your contact model. It means a little bit of force at a distance. It means a little bit more penetration, but you can soften your contact model in a way that has a similar effect, like almost an equivalence. We can, for any noise sampling model in RL, we could find a contact model, but they might be weirdly shaped, okay? Is stochasticity essential? And it turns out you can do deterministic smoothing, and you can put that into like an RRT kind of planner for contact, which never worked for contact before. RRTs motion cones are good, and so there's a couple examples, but RRTs have not had the success you might think in planning through contact before. but they work a lot better if you just smooth out some contacts. It makes the distance functions work better. I could tell you more or less of the details. But this lights me up. This is like something amazing happened in RL, empirical RL, and now I think the theorists are coming in and understanding it a little bit better, and sometimes the answer will be not just RL, but a mixture of RL and true gradients and models. And I would put my money on that being the future, because there's just I mean, Go maybe has some structure, but it doesn't have an obviously interpretable structure to me. Like if I take a picture of a Go board and I move one piece, the rollouts could be completely different in ways that I don't have enough Go skills to understand, okay? But if you take my robot and my environment and you move me by a centimeter, it's gonna be pretty similar. It better be, otherwise I'm in trouble. So I think the structure in those problems has to matter. All right, that concludes RL day one. We'll talk a little bit more about maybe model-based RL, and we're actually surveying you on this P-set about what you want to see in the next few lectures. So tell us, and we'll dial it in.